All right, so 8.2 is where we're looking at. What we're looking at today, properties of parallelograms. And it says a parallelogram is a quadrilateral with both pairs of opposite sides parallel. We can use shorthand for parallelogram. You know how when we name triangles, we draw a little triangle? Well, when you're going to name a parallelogram, you'll do a little slanty box. Wow, that's not very good, but you get the idea. Draw a little slanty box, and that is the universally accepted symbol for parallelogram. And we're going to just learn a bunch of stuff that results from the fact that if you take a quadrilateral with both pairs of opposite sides parallel, there's all sorts of relationships that result. And the first one is this. Theorem 8.3 says, if a quadrilateral is a parallelogram, comma, then it's, I don't think apostrophe belongs there, does it? It doesn't. Yeah, I don't think it does. Then it's opposite, well, is it possessive? I don't know.
If it's possessive, there's no.
If it's possessive, there's not one.
Yeah.
Only if it's a contraction. Because it's not like it's James's or whatever. Okay. All right. So then it's opposite sides are, well, that by definition, yeah. By definition, we know that. If it's a parallelogram, we know that. But what other, let's draw a picture. So if, what? Let's take a look. So remember those lines like that? Let me zoom in a little bit. This is kind of tiny. The little arrows show that these sides are parallel, and then we'll do double arrows here because they're not all parallel to each other, right? Just the opposite ones. But yeah, it turns out if quadrilateral PQRS is a parallelogram, then yeah, I heard some people say it. Then it turns out these opposite sides are congruent. PQRS. And then how can we show in a picture that they're congruent? Tick marks. But we just want to show opposite sides are congruent, right? So PQ and SR, we'll do a single tick mark, and then what should we do for the other ones? Yeah, double tick marks. Because we're not saying that they're all the same, just opposite sides are congruent. All right, are congruent, there we go. And that's pretty intuitive when you see a bunch of these. Theorem 8.4, if a quadrilateral is a parallelogram, then its opposite angles are, guess what? Its opposite angles are congruent. And I think when you got a picture, you can kind of see that because aren't these both, they both appear to be obtuse, don't they? And these both appear to be cubed. So it's a little bit intuitive. So let's draw a little picture here. Let's go if, and we'll draw a little parallelogram again. P, Q, R, S. If you have a parallelogram, then redraw it. P, Q, R, S. And how do we show that angles are congruent? Arc marks. But they're not all the same, are they? Just opposites. Just opposite angles are the same. So let's go, you can either go double arc marks, or you can do an arc mark with a tick mark. Let's do that. All right, are you guys cool with that?
Yes.
Okay. So I'm going to do some proofs in our notes, but I'm not going to make you guys do proofs on our quizzes and tests. I might make them a bonus though. So I just kind of, make sure you're following along with the proofs. It's a good lesson in life to not always accept things at face value, right? There should be some kind of justification. So what we're going to do real quick is, and this is kind of a shortened proof. It would actually be a few more steps, I think, if you were to do it proper like. But let's prove theorem 8.3. Let's prove that if you've got a parallelogram, then the opposite sides are congruent. And so it says that we're given a parallelogram. Let's draw a picture just to have something to look at here. And it's parallelogram A, B, C, D. Draw some arrows on there so that we know it's a parallelogram. That's what we start with. And yeah, then we always start with the given. So up here for our reasons, just write down that we got a parallelogram, right? Parallelogram A, B, C, D. We start there, and we're trying to prove that AB is congruent to CD and that BC is congruent to AB. And how you go about doing that is by using some stuff that we've learned before. What we're going to do is we're going to split this up into a pair of triangles. And as soon as we do that, we're going to be able to realize some relationships. Basically, how we're going to get there is we're going to prove that these two triangles are congruent. And if these two triangles are congruent, what do we know about corresponding parts of congruent triangles? They're congruent. So that's the way we're going to go about this. But how can we show that this triangle is congruent to this triangle? Say what now? Okay, so
Opposite angles.
okay, opposite angles. All right. Now it sounds to me like you're using theorem 8.4 and using theorem 8.3, but aren't we trying to prove theorem 8.3? Okay. Now there's something that I can work with. Don't we know that this angle and this angle are congruent? Because parallel lines cut by a transversal, alternate interior angles are congruent. So we're going to know that angle BAC is congruent to angle DCA. Additionally, what else do we know? For the same reason.
DAC is congruent to BCA.
DAC is congruent to BCA. Just looking at different parallel lines, right? These parallel lines cut by this transversal, alternate interior angles are congruent. Okay, so let's document that in the same line there. Sorry, you gotta write small today. DAC congruent to BCA. And alternate interior angles theorem is our justification. Well, is angle enough to prove triangles are congruent? Angle?
No.
Angle proves they're similar, doesn't it? Do you guys remember that? That was actually part of the bonus on the test. So, what else can we know to show that triangles are congruent? What else can we use? Say what?
The middle line.
Oh, the middle line right here?
Yeah.
Yeah, okay, so is this line here going to be congruent on both triangles?
Yes.
Yes, so I'm going to put a tick mark on there. gonna say that AC is what?
Congruent to AC.
Congruent to AC by what justification?
Reflexive property of
Oh yeah, reflexive property of congruence. And at that point, ladies and gentlemen, we can prove that triangle ABC. Now let me get this, make sure I write it right. If I go ABC, how do I have to write the other one?
ATC.
Oh, I gotta go C, don't I? CDA. Triangle CDA. I know those two triangles are congruent by what justification? Angle side angle. Very good. And angle side angle congruence. I can't remember if it was theorem or postulate. We'll just say angle side angle. We'll just leave it. We don't want to complicate things. All right, ladies and gentlemen, now that we know that these two triangles are congruent, what do we know about AB and CD? Yeah, AB is congruent to CD, and what else? BC is congruent to AD, and that is because corresponding parts of congruent triangles are congruent. Well, would you guys agree that this also, you could very easily adjust this proof to, I mean, couldn't we also say some things about the angles now too? Can't we say angle B is congruent to angle D by CPCTC, right? You could expand it, and then you could talk about, there'd be a little more involved talking about these two. You'd have to do like an angle sum property. But yeah, that's how you can justify all these relationships, at least these two relationships. Well, let's actually put this into some use here. Example 1 says find the values of x and y. Well, let's look at x first. By the way, these arrows tell us this is what kind of shape? Parallelogram. If we're going to find x, what can we do?
Theorem 8.4, so it's equal to angle H.
Yeah. Opposite angles are congruent. I guess we'll write that down real quick. Opposite angles congruent. So x is equal to 72, isn't it? That's kind of nice. Well, what else? To what?
Y is equal to 44.
Y is equal to 44 because opposite sides congruent, right? So y minus 8 has to equal 36, and you can quickly solve for y. Are you guys cool with that? Now, they can make things complicated a lot of different ways. They could say, well, one side is, I'll take that back. But there's lots of different ways that you can set these up. So just kind of be on your toes and be thinking about each problem separately and kind of thinking what they're trying to say. Now, something I want you to notice is that we got this nice picture here. This might be a good opportunity to see this. Since we got parallel lines, can you think of HK as being a transversal? Parallel lines, transversal. What do you know about these two angles?
They're supplementary.
Yeah, they're not congruent, but they're consecutive interior angles, and they're going to be supplementary, aren't they? So that kind of leads us to our next property that we're going to look at. And example 2 is it's actually an application of that. So read through example 2 and see if you can figure that out. So based off of what I just told you, if LMN is 110, What's the measure of angle MNO?
70 degrees.
70 degrees. So, go ahead and get this down. Consecutive, there we go. Is that right? Yeah. Consecutive angles are supplementary. So 180 minus 110 gets us 70 degrees. All right, let's look it over. I think that's another theorem. So let's get this down. If a parallelogram, we'll get rid of the quadrilateral part. Everybody knows these have four sides, right? Okay, so if a parallelogram then
We just left out the quadrilateral.
yeah, we just left out the quadrilateral part. So if it's a parallelogram, then its consecutive angles are supplementary. And so just draw a quick picture here. P, Q, R, S. And then draw in your parallel lines there. And put an X at angle P and then Y.
Can you shoot your picture, guys?
Oh, yeah, that'd be helpful, wouldn't it? Yeah. Thank you, sir. If a parallelogram, then its consecutive angles are supplementary. So what do we know about X and Y? Equal 180. Pretty cool, huh? All right, let's jump into the last one, the last relationship. If a parallelogram then its diagonals, so this is kind of interesting. It's diagonals, so let's draw a picture here. Maybe we can guess what's going on. So if you've got a parallelogram and you draw the diagonals in, take a guess at what happens with the diagonals.
Opposite triangles are congruent.
No.
Oh, so like this and this? I think that might be right. Yeah, I think that might be right. But that's not what we're getting at. We're going to say something specifically about the diagonals. But actually, what you say in there does help. If these triangles are congruent, what do you know about the measure of this angle, or this side and this side?
They're congruent.
And what about this side and this side?
Oh, the diagonals bisect each.
Exactly. If a parallelogram, then its diagonals bisect each other. All right, yeah, they bisect each other, so you can go tick mark there. And then are we saying that they're all the same? Are these diagonals both the same measure?
No.
Nope, so we'll go double tick marks there. You guys cool with that?
Yes.
Okay, so let's kind of see what else we can do with this. Example 3 says the diagonals intersect at point T. What are the coordinates of point T? Oh, okay. Well, first things first, is this a parallelogram?
Looks like it.
It looks like it. How can we know for sure?
The sides are.
Yeah, are these two sides parallel? They're both horizontal, so yeah, they are. What about these two?
They have the same slope, so yes.
Agreed. They both have a slope of 3/2, don't they? So if they have the same slope, we know that these are parallel as well. Okay, so we've learned that, we just now learned that if it's parallelogram, the diagonals bisect each other. But how does that help us get the coordinates of T? I mean, I could guess at it, and I'd probably guess right, to be honest. Doesn't it look like it's at, what is that, 1, 2, 3, 4, 5? 5.5 up 2.5. Do you guys agree that that kind of looks like? But I want to be a little more certain than that. It turns out that if we know that this measure is equal to this measure, T is the midpoint, isn't it? And we learned a midpoint formula a while back. And it's actually pretty straightforward. Does anybody remember, given 2 points, how you find the midpoint? You basically take the average of the two coordinates. So P is at 2, 1. R is at 9, 4. And the midpoint formula says you add the x's together and divide by what? 2. That's how you get the average of things, or two things at least. And you add the y's together and divide by what? 2. So the midpoint formula is just saying add those coordinates up, divide by 2, and sure enough, our midpoint, which is actually a t, isn't it? All right, t. 11 divided by 2 is 5.5. And 5 divided by 2 is
2.5.
2.5. So because they bisect each other, that's a midpoint relationship. It's in the exact middle. So you can do the midpoint formula. And why don't you guys work out example 4, and I'll be quiet, and I'll take roll, and then I'll work it out. See if we agree. And once you feel good with example 4, we'll move on to example 5. If you're impatient, you could check with a neighbor and see if you guys agree and stuff. I shouldn't say you're impatient, but you just want to know. Just want to know a little bit. Boy, NBD, right? No big deal. You guys good with that?
Mm-hmm.
Yeah? Let's go on to example 5. Find the indicated measures. That sounds more complicated. Measure of angle BCD. BCD. Okay. Well, gosh. Any ideas for BCD? So we're talking about that whole angle, right? Emery, what you got?
We can know that BDC is 100 degrees because of alternate interior angles.
Okay. I agree. Oh, yeah, so this whole thing's 137. Oh, okay, so we know that these two angles combined would be 180, and one of them is 137. Yeah, I'm with you. And what is that? 180 minus 137. Was it 43? Yeah, right on. So we did have to kind of think a little bit. Emery said alternate interior angles to get that. I like it a lot, yeah. And then another way you could have gotten there, I suppose, is alternate interior angles here is 37. And don't we also know that the sum of all these angles is 180? Because it's a triangle. So yeah, there's a couple of different ways to get there. I dig it. So 43 degrees. Okay, so let's try this next one. If BE equals 9, find BD. BD's 9 as well?
ED is not.
Wait a second. Yeah, BE is half of it, isn't it? So the other half's 9. So BD would be what? 18. Little sneaky, wasn't it there, Jackson? Little sneaky. Well, all right, so just to review this real quick, if you have a parallelogram, we know it has basically 5 different properties. The first one's the obvious one. Opposite sides are what?
Parallel.
Parallel. Opposite sides parallel. That's a by definition one. It's not a parallelogram unless this is the case. Opposite sides are parallel. But what else do we know?
Opposite sides are congruent.
Yeah, opposite sides congruent. What else do we know?
Opposite angles.
Opposite angles congruent. What else do we know?
The diagonals bisect.
Diagonals bisect each other. Diagonals bisect each other. Anything else?
Consecutive angles are supplementary.
What is that?
Consecutive angles are supplementary.
Consecutive angles supplementary. Yep. Consecutive angles are supplementary. There's a lot going on, isn't there? Okay, so ladies and gentlemen, the practice for this is page 518, and it's numbers 3 through 35, and then you jump over to 38 through 40. If you feel like that's too much, what could you do?
Odds.
Yeah, you can do the odds. I think these will be pretty quick though, so you know, do what you want. But the important thing is you want to practice, and just so you kind of plan ahead, we're going to learn about 8.3 tomorrow, and maybe get our tests back as well. And so I'd like to quiz on probably on Thursday over 8.2 and 8.3. Okay, 8.3 is proving things are parallelograms, so it's kind of going backwards with some of this stuff.